Hi, everyone. Today I'm going to talk to you about BeeBox, hardening BPF against transient execution attacks. This is a joint work with my lab mate Alexander Gaidis and my advisor Vasileios Kemerlis. So we have been using the model of strong separation between OS kernel and the applications for several decades, and this model can be at odds with the ever-growing performance requirements. BPF bends the line of this separation and allow the user to put application logic into the kernel. But it has been shown that BPF itself does not, even if BPF itself does not introduce vulnerabilities, it can amplify security problems in the kernel, one of which is transient execution attacks. In BeeBox, we are proposing a new framework for hardening against such attacks. BPF was invented for user applications to safely delegate computations to the kernel. Think of it like JavaScript for the kernel, but a little bit safer. It is defined as a small virtual architecture with a RISC-like instruction set. It has a lot of applications in networking, profiling, high-performance storage, and other areas. BPF's instruction set contains typical instructions like ALU, memory accesses, conditional branching. The safety of such BPF program composed of BPF instructions is statically verified when the BPF program is loaded into the kernel. The verifier tries to make sure that this program always terminates and it does not access unintended memory. For runtime performance, BPF nowadays are usually always JIT compiled to run. And at runtime, BPF has access to BPF helpers, which is a predefined set of native kernel functions that are called from BPF. BPF context, which is the data passed from the kernel to BPF. BPF stack, which is the scratch space used to store local variables. And BPF map, which is a collection of persistent data storage that BPF uses to aggregate results. BPF has been known to cause trouble with transient execution attacks, which I will briefly summarize here. Due to optimizations like out-of-order execution and speculative execution in modern CPUs, sometimes an execution of an instruction needs to be squashed and discarded instead of being committed. And these instructions are called transient instructions. On the one hand, these transient instructions may not follow the semantics intended by the programmers, but on the other hand, these transient instructions are not fully transient in the sense that they leave behind various tracks in various internal CPU states, such as cache, which can be later recovered through side channels. These two things combined means that even the program is perfectly correct, the CPU can still leak information that's secretive. The transient execution attack is particularly deadly in combination of BPF because the attacker can inject native code patterns into the kernel and control their execution trace, while also have access to a less noisy signals in general and bypass some defenses targeting cross-domain attacks naturally. Linux has defenses against transient execution attacks in its BPF implementation. In this, we call them Linux provisional mitigations, or LPM for short. The main idea includes letting the verifier verify all branch and value combinations in its static analysis, so that it can prevent unsafe behavior in speculation. LPM also inserts speculation barriers to prevent incorrect speculative store bypass. LPM has a couple of limitations due to this. It breaks compatibility and rejects legal programs because of the additional static analysis needed for the speculative behaviors. It also causes large overhead when the BPF program is complex and speculation barriers are required to be inserted. And with BeeBox, we aim to address these issues. The first goal of BeeBox is to defend against Spectre-PHT, known as Spectre v1, and Spectre-STL, also known as Spectre v4. Similar to LPM, BeeBox leaves other instances of transient execution attacks to the generic defenses deployed in the kernel. The second goal of BeeBox is to maintain full compatibility and not having additional constraints on BPF programs. And the third goal is to be efficient and performant. The key idea is quite simple. BeeBox tries to allow any speculation or misspeculation, but sandbox all of the memory accesses made by the BPF programs such that no sensitive data, in this case kernel data, will be exposed during the speculation. The way we sandbox the BPF runtime is using techniques from software-based fault isolation. We will have 4 GB sandbox region for each user, and during the execution of a BPF program, a dedicated register will always point to the base of the sandbox. Then the BPF pointers and their dereferences during the JIT compilation process will be transformed with instrumentation such that they always point into the sandbox. Lastly, we're going to move all of the data that's needed by BPF programs runtime into the sandbox, including the stack, the maps, and the context. The exact instrumentation is shown here. On the left is a hypothetical BPF snippet. It first loads a pointer, then it adds some offset to it, then it dereferences it. In the vanilla kernel, it will translate to instructions shown in the middle. If R3 or RCX after translation is speculatively out of bound, then the dereference can potentially leak sensitive data in the later execution because it can speculatively load sensitive data into RDX. But on the right side is how we JIT compile them under BeeBox. Firstly, at the beginning of the BPF program, we load the base of the sandbox into the dedicated register, which is R12 here. Then the pointer is transformed into a 32-bit value, which is hex 1000 here, representing the offset starting from the beginning of the sandbox. Then the actual dereference is translated into 2 instructions. Move ECX to ECX will clear the upper 32 bits of the register, making sure that it's between 0 and 4 GB. Then the next instruction will add this to the base register and read the memory. Regardless of what value speculatively RCX is before the yellow instructions, the actual memory being dereferenced will stay in the sandbox. Now let's look at the data that we're putting into the sandbox. BPF stack is only used by BPF programs, and it needs to be allocated every time a BPF program is invoked. The BeeBox has a pre-allocated region to act as a stack for this, such that it can be open and closed with a stack pointer change. For BPF maps, they contain user data, but it can also have in the data structure the data structure can also contain kernel metadata such as raw pointers. As a result, the maps need to be split into 2 data structures. The metadata needed by the kernel will be placed outside of the sandbox, and the actual data that's visible to BPF will go inside the sandbox. The BPF context is generated by the kernel, and then later, therefore, it needs to be copied into the sandbox. And the memory management part, it can reuse the pre-allocated region that we have for BPF stack because it's needed every time a BPF is invoked. But copying context can be costly in the world of BPF. So we have some domain-specific optimization that leverages BPF's simplicity and analyzability to reduce such cost. BeeBox RC tries to only copy context fields that are needed, identified through static analysis. This can be applied to most types of BPF programs. BeeBox RB is applicable when the context's entire page should be semantically accessible to BPF. Then we can just map it into the sandbox whenever the page is allocated, therefore avoid the copying. BeeBox CP tries to avoid transforming the context pointer altogether. This can only be used when the context pointer cannot be speculatively hijacked. This is applicable to BPF program types that have simple context usages. There are a couple of other interesting things that we'll not go into here, but are details of which are available in the paper. So let's look at some evaluation results. This shows a synthetic micro-benchmark that we created with BPF programs that stress different kinds of BPF access pattern. These 4 bars are no mitigation, LPM, and 2 differently optimized BeeBox schemes. The most optimized version of BeeBox has on average, not on average, has 0 to 23% overhead, where it tends to be higher when the BPF program is helper heavy, whereas LPM has over 200% overhead when the BPF program is stack heavy because it inserts speculation barriers for stack accesses. We also test Katran's performance using their performance suite. Katran is a load balancer, and each benchmark here represents a different kinds of incoming traffic. BeeBox on average incur 20% overhead, while LPM incurs 112% overhead. We also tested BeeBox with some cBPF workload, and the overhead on average is less than 1%. To conclude, BPF is an important kernel feature that is prone to transient execution attacks. BeeBox mitigates the problem by sandboxing the BPF runtime. BeeBox is efficient and more secure while maintaining full compatibility, and the artifact is available on GitLab, and thank you very much.